Hey everyone. So in this video, we're going to try and understand the chain rule of differentiation, which is used to differentiate complicated functions like the one you see. So what does the chain rule tell us? The chain rule is actually a very simple principle which tells you that given a function y, which is dependent on x, and then if you have a function z that depends on y, which as you know means that now z implicitly depends on x through y, then you want to calculate the derivative of z with respect to x. If you want to try and find its sensitivity with respect to x, you can say the derivative of z with respect to x is equal to the derivative of z with respect to y times the derivative of y with respect to x. So you can differentiate these two functions with respect to the variables that show up explicitly, and in turn, by chaining the derivatives together, get the derivative of z with respect to x. Now, let's look at an example and it'll become clear how this is so useful. So we've got this function z of x is equal to e to the power of 3x squared plus 2x. Obviously, you don't see a y here, right? Now, this kind of function is called a composite function because what you can do is write it as a function of a function, right? What do I mean by that? Well, you can say let y of x is equal to 3x squared plus 2x, right? And so now this term is y. And then z of y is e to the power of y, where we know y is 3x squared plus 2x. So z is now a function of y, which is a function of x, right? And so now because you've got two simpler functions, let's write this in the form of a graph. You have x and you have y goes into this first function, right? And so what you get is y, and what you do to x is multiplied by 3, square it, so 3x squared plus 2x. And then the second function where this y now goes into this function and it's raised to the exponent, right? So the exponent is computed and what you get is z. So we have broken this function down into two simpler functions. The advantage is now you can take the derivative of these functions quite simply, right? Because they are, basically the rules, simple rules of differentiation apply here. So in this case, the derivative of y with respect to x, right, is the derivative of 3x squared plus 2x with respect to x. So what you get? You get the derivative of 3x squared is 6x, and the derivative of 2x is 2. So you get this differential or this derivative. What you have next, you have the derivative of z with respect to y. Now, again, it's a very simple function, and we know that the derivative of e to the power of y with respect to y is e to the power of y. So we've got the derivative of these two simple functions. And now, chain rule tells us that the derivative of z with respect to x is dz dy times dy dx, right? Now, what is dz dy? It's e to the power of y, so we can write that there. What is dy dx? We've just calculated that. It's 6x plus 2. We can bring that there. And you have the derivative of z with respect to x. Now, of course, here we've got y here. What we can do is, if we want substitute for y, we know y is 3x squared plus 2x. So we can bring that in. And you have dz dx is the exponential of 3x squared plus 2x times 6x plus 2. So by taking this composite function, but now converting it into simple function and then a second simple function, and kind of breaking it into this simple chart-like structure, what we've ended up is being able to compute the simple derivatives analytically and then chaining it together to get the derivative of the composite function. Now, what this becomes very powerful for is when you have much more complicated functions. So you have this function here, g is e to the power of this complex term. Applying the same principle, what you can do, and this graph-like approach makes it very easy, you can just take the first term, let's say this is a, let's say 3y minus 2 is b, and so now you have e to the power of ab plus z, let's call that f, and what you end up with is g is e to the power of f. So we've broken this or down into a chain of simple functions. Now we want, let's say, the derivative of g with respect to x, right? So we know that x comes into g, or g depends on x through this part. It comes in with a. So what we can do is say first, using chain rule, the derivative of g with respect to x is the derivative of g with respect to f, and g only depends on f directly. Then the derivative of f with respect to a, right? It's a partial because it depends on a, b, and z. and then the derivative of a with respect to x. A only depends on x. And if you chain these three derivatives together, you get the derivative of g with respect to x. So we see how the chain rule can help us find the derivative of fairly complicated functions, right? By allowing us to break it down into simpler functions, finding the path of dependence, and then computing the derivative, right? By chaining together the derivatives of the simpler functions. So hopefully this has given you a good understanding of the chain rule and you're ready to apply it where you see it. For example, when you're kind of building neural networks and are looking to backpropagate. Thank you.